Today we will go over our test review for the mole composition unit. And as always, what to study. You're going to study your homework. You're going to study your notes. You're going to study bell ringers. You're going to study all of the quizzes that you may take this unit. And maybe even a lab if we get to it. So the test is actually not going to be as similar as the other tests have been. There's not like a lot of matching. It's just a bunch of calculations, that's all. So here are some sample questions to look at as you are studying, and I'll walk you through them. So first question, how many atoms are equal to this many moles of carbon? So we are going from particles to moles. So that was one of our simpler equations. So how many atoms are equal to this many moles? So our known and our unknown. So the known is what the question gives us, 4.61 moles of carbon. Unknown is how many atoms. So how many atoms of carbon? Okay, so we always start with our known first. So our known is 4.61 moles of carbon. Okay, and we need to cancel out moles. So whatever's up here must go here. Moles of carbon. And then up here we are trying to get to atoms. Since we already have moles, we don't need to, it's not a two-step conversion, it's just a one-step conversion. So atoms of carbon. So for every 1 mole of carbon, the conversion is that there are 6.02 times 10 to the 23rd atoms of carbon. And then we just calculate it and we have our answer. So it is 4.61 times, okay, yeah, you got to turn your calculator on. 4.61 times 6.02 times 10 to the 23rd. Okay, and that equals that many atoms. Okay, if you're giving atoms and it's not this crazy number, you can probably bet that you've done something wrong. So, look at your significant figures. You should have 3 significant figures. So 2.78 times 10 to the 24th atoms of carbon should be your answer. Moving on to the next one. How many moles are equal to 1.27 molecules times 10 to the 23rd molecules of water? So our known, 1.27 times 10 to the 23rd molecules. You cannot see that, I'm so sorry. Molecules of water. The unknown is how many moles of water? So again, it's not a two-step equation because moles is already involved. We're already given moles. So you start with your known, which is 1.27 times 10 to the 23rd molecules of H2O times equals. So we have, this needs to go down here. And what we need is up here. So for every 1 mole of H2O, again, it's just a conversion factor. It's just like saying for every kilogram, it's 1,000 grams. 6.02 times 10 to the 23rd. This should become routine for you guys by now. Okay, and you take your calculator. 1.27 times 10 to the 23rd times 6.02 times 10 to the 23rd. All right, and I did it wrong. I was supposed to divide. So let's go fix that. Sorry, guys. Times 10. Divided by Okay, so I fixed it, and the answer should be, so these units will cancel out, so molecules of H2O, molecules of H2O cancel out, and we're left with moles. So the answer will be 0.2. We have three significant figures, so 2.11 moles of H2O is our answer. Okay, next question. How many moles are equal to this many grams of potassium oxide? So again, known and unknown. We are dealing with moles, so it's not a two-step conversion. The only time we have a two-step conversion is when we are not given or going to moles. If we're not given or going to moles, we will have a two-step problem, like mass to moles. Nope, not this one. I'm sure we will encounter one. So our known is 47.2 grams of K2O. Our unknown is how many moles? Okay, so I always write my known first, which is 47.2 grams of K2O. Times and equals. So whatever's here must go down here, grams of K2O. And whatever's up here is our unknown. Unless it's a two-step conversion, then we have to do something else. Moles of K2O. So basically we have to find out how much this thing weighs. So for every 1 mole, this thing has a mass. And to figure that out, we must add its mass. So this is where we go to the side and we do potassium and oxygen. We have 1 potassium, and we have, okay, my bad, we have 2. It's getting time to be done. So we have 2 potassiums, and we have 1 oxygen, okay? So potassium, according to the periodic table, has a mass of 39.098. 39.098. So 39.098. And each oxygen, we should have this memorized by now, is 15.999. But no, you don't have to memorize it. I'm just saying you've used it enough. Okay, we're going to multiply and then we'll add the 2 together. So on my calculator, we'll do parentheses 2 times 39.098 plus 15.999. I did not need the parentheses, but 94.195, and we're going to keep it that way. So 94.195 grams. Now all we have to do is take this number, 47.2, divided by this number, 94.195. And the answer with correct significant figures is 0.501. These units cancel out and we're left with moles of K2O. That's our answer. Okay, moving on. Last question of the page. What mass of calcium nitrate is equal to 0.75 moles of this substance? So our known and unknown. So known is 0.75 moles of CaNO3,2. Our unknown is what mass? I'm sorry, and it's actually in grams. I should have done that in the first place. CaNO3, 2. Okay, and we just do our thing. Okay, so we start with our known, which is 0.75 moles of CaNO3, 2. Multiply it. It's just one step because we have moles, or we're going to moles. In this case, we have moles. So we need to cancel out the moles. So mole of CaNO3, 2. And up here is going to be mass. So we'll have grams of CaNO3, 2. Okay, so all we need to figure out is how many grams for every 1 mole of this stuff. So how we do that, we go to the side and we have calcium, we have nitrogen, and we have oxygen. We have only 1 calcium, we have 1 nitrogen, but times 2 because of the parentheses, so we have 2 nitrogens. Oxygen, we have 3 of them, but there's 2 of them, 2 of those 3, so there's actually 6 oxygens. Okay, and now we just go to the periodic table, find out how much they weigh. Calcium has a molar mass of 40.078. And nitrogen has a mass of 14.007. And oxygen, 15.999. Multiply and then add them together and we'll have our molar mass. I don't know what's easier for you. Okay, so we don't have to multiply by that, so we will put 40.078 plus 2 times 14.007 plus 6 times 15.999. And the answer is 164.087. It's 086. Okay, so we just plug that in here. 164.086. Easy. And then we just plug this into the calculator. So we have 0.75 moles. We're going to multiply it by 164.086. The answer is, we need to look at significant figures, 2 significant figures, so we actually have to round this up. So it's going to be 120. 120, these units cancel, and we have 120 grams of calcium nitrate. That's our answer. All right. Next, what volume would this many moles of gas occupy at STP? So we're going from moles to volume. So our known and unknown. So our known is 0.358 moles of nitrogen gas. And our unknown is what volume, how many liters of nitrogen gas. So we always start out with what we know, which is 0.358 moles of N2. So whatever's up here must go here. And for every 1 mole of for every 1 mole of any gas, we have 22.4 liters of that gas. So all we have to do, 0.358 times 22.4. And our answer with significant figures in consideration is 8.02 liters, because this unit cancels, of N2. Okay, next question, how many moles of carbon monoxide gas would occupy this much? So another gas question. So we have the, our known is the amount, the volume, liters of CO. Our unknown is how many moles is that? How many moles of carbon monoxide do we have? So we write our known first. I'm going to scoot this up now. We write our known first, which is 17.24 liters of carbon monoxide. Okay, whatever's up here must go here, liters of carbon monoxide. And we need to go to moles, so 1 mole. So for every 1 mole of carbon monoxide, we have 22.4 liters. It's just a constant. It's just like, again, saying for every kilogram, we have 1,000 kilograms. Kilometer and meter might work, and it is kilometer. All right, so we have this 17.24 divided by, and you can't see this, I'm sorry, divided by 22.4. And that equals, with our correct significant figures, 0.7696. So 0.7696. These units cancel. We are left with moles of carbon monoxide. Okay. Next, how many molecules of S2 gas would occupy 4.15 liters at STP? So here's the first example of a two-step conversion. So we have we want to know molecules, and we have volume. So we don't have moles, and we're not given moles, and we're not going to moles. So now we must use the moles in the middle as a conversion. That's how you know if you have a two-step problem. So you have known, you have unknown. Known is what they give you in the problem, 4.15 liters of SO2, sulfur dioxide, and then we want to know how many molecules of sulfur dioxide that we have. Okay, so this is a two-step problem. First, we need to go from what we know to moles, and then moles to what we want. Okay, so what we know, 4.15 liters of SO2. Two-step problem. Okay, so down here, whatever's up here must be here, liters of SO2. And then we need to convert to moles of SO2. So for every 1 mole, 22.4 liters, that's just conversion, that's easy. Whatever's up, so these units cancel, and then we're left with moles. Now we need to put moles, whatever's up here, we put down here, 1 mole of SO2. And our unknown needs to go up here, which is molecules of SO2. So for every 1 mole, we just use Avogadro's number to convert to molecules. It's 6.02 times 10 to the 23rd. Okay, and we just calculate it in our calculator. So we have 4.15, and since this is on the bottom, divided by 22.4. And this is on the top, so we're going to multiply by Avogadro's number. Why did I do 2? 6.02 times 10 to the 23rd. And that equals 1. Let's look at significant figures. 415. So 3 significant figures. So 1.12. We have these units canceled, so we are left with molecules of SO2. Molecules of sulfur dioxide, and there's our answer. Moving on. Do you need something, bub?
Yeah.
What?
I want a piece of gum.
But I don't have any gum.
There's gum in the trash can.
There's gum in the trash can? I have no idea where it came from. I'm sorry, I don't have gum. All right, what is the mass of this mini formula unit? So again, we're not given moles, and we're not going to moles. So this is a 2-step conversion. So we have known, unknown. So the known is this, 2.31 times 10 to the 23rd. Formula units of strontium fluoride. Okay, unknown is the mass. What, bub? Okay, love you. Okay, so we always start with our known. Our known, which is 2.31 times 10 to the 23rd formula units of SrF2. Okay, so whatever's up here must go down here. So formula units of SrF2. And we need to convert to the mole because that's kind of like the middleman. Moles of SrF2. We can go ahead and fill this out if we want. For every 1 mole of anything, you have 6.02 times 10 to the 23rd particles or formula units or atoms or molecules, whatever we're talking about in the problem. And these units cancel. Now we need to, whatever's up here must go here. So 1 mole of SrF2. That should be an equal sign. Our unknown is grams of SrF2. So basically, these will cancel out, and we need to find out how many grams of strontium fluoride are in every mole. So we just come over here. So strontium is 87.62 grams per mole. There's only one of them. 87.62. Oh, that's really ugly. I'm sorry. Okay, and then we have fluoride, which is, you can't see, 18.998. We have 2 of them, 18.998. So we're going to add those 2 together, and then whatever it is, we put in here. Okay, so we have 87.62 plus 2 times 18.998, 125.62. So what we put here is 125.62. Now all we have to do, plug these numbers in the calculator, and we have our answer. So we have 2.31 times 10 to the 23rd divided by 6.02 times 10 to the 23rd times 125.62, and the answer is 48. We have three significant figures, so 48.2 grams of strontium fluoride. And that's our answer. Okay, last question on this page. What is the volume of 13.21 grams of ethanol gas at STP? I'm sorry, ethane, not ethanol. So it gives us mass and we have to go to volume. Again, we don't have moles. We're not given moles. And we're not going to moles. So it is going to be a two-step problem. So we have a known and we have an unknown. The known, this thing, 13.21 grams of C2H6. I will say one thing and my hand just does whatever it wants. Okay, unknown. What is the volume? What is the volume of C2H6? Okay. Okay, now let's just write it out. We have our known, which is 13.21 grams of C2H6. We need to convert to moles, then liters, and we're done. So here, grams of C2H6, and we will need to convert to moles. That's our middleman. Again, we've said this. Then whatever's up, these two will cancel out. Whatever's up here needs to go here. 1 mole of C2H6. And we are looking for liters of C2H6. And this is just a constant, so we'll go ahead and put that. And while I'm here, I'm sure I've said it in class, but just in case if I forget, when we say liters, we're only talking about gas. We are not talking about volume of a liquid. We are talking about volume of a gas only. Just to be clear, I'm sure I have made that clear in class, but just in case. All right, so now all we really have to do is calculate what the molar mass of this thing is. So we have carbon, and we have 2 of them. And we have hydrogen, and we have 6 of them. So carbon weighs 12.011. Hydrogen weighs 1.008. Add them together, and whatever that is, we'll put right there. Okay, so 2 times 12.011 plus 6 times 1.008, 30.07. So we will plug, yeah, whatever, we'll leave it. 30.07. Okay, so we are done filling this in. These units will cancel. We'll be left with liters of ethane, which will be what we want to find out. So we just plug in our numbers now. 13.21 divided by, since this is on the bottom, 30.07. This is on the top now, multiplied by 22.4. And our answer is 9.8 with 4 significant figures. So 9.841 liters of C2H6. Last page. What is the percent aluminum in, I don't even know, aluminum chromate, maybe. All right, doesn't matter its name. The percent of aluminum. So first, we find out how much it weighs. So we have aluminum. We have chromium. And we have oxygen. So what we'll do, okay, we have aluminum, which we have 2 of, and we will multiply by how much it weighs. Chromium, we have 1, but we actually have to multiply it by 3. Oxygen, we have 4, but we need to multiply that by 3. Okay. So aluminum, 26.982. Chromium is transition middle. Here it is, 51.996. Oxygen, 15.999. And we will add them together. Okay, so 2 times 26.982. Why did I do that? It doesn't matter. I mean, that's fine, but why did I do the parentheses? I was about to just add them all, which we will do, but okay. So we actually need the individual masses. 53.964. We technically could just stop since we're only trying to find this. Yeah, I guess I'll do that. That way it'll be quicker. So we have our mass of aluminum. Now we just need to find the mass of all of it. So 2 times 26.982 plus 3 times 51.996 plus 12 times 15.999. So the whole mass is 401.94. So now all we have to do is take 53.964 divided by 401.94. So we have 0.13425 whatever. Remember, we need to multiply it by 100. You could just move the decimal over. I always feel comfortable multiplying it by 100. So 13.43%. So the answer is 13.43% aluminum is our answer. Okay, find the percent composition for each element in this compound. So we basically do this, but now we actually have to multiply sideways for all of them, which is fine. Okay, so we have zinc, we have chlorine, and we have oxygen. We have only 1 zinc. We have 1 chlorine, but we have to multiply that by 2. We have 3 oxygens, but we have to multiply that by 2. So zinc's mass, somewhere around here. Here it is, 65.38. Chlorine, 35.45. Oxygen, 15.999. Okay. We will have to add all of them up together and get the whole. So we'll go ahead and do that first. So that's, we don't have to do that. So 60, but I still did it. 65.38 plus 2 times 35.45 plus 6 times 15.999. So 232.27 is the molecule's mass, but we still have to do this. So this is brought over, and this will need to be brought over, and so will this. So to find out the percent composition of each, we'll just do it one at a time. So we'll take 65.38, because there's only one, we don't have to multiply it by anything, and divide it by the mass of the whole molecule, which is 232.27. We take that and we multiply it by 100, and we'll have our percent composition. So we will do 65.38 divided by 232.27, and we can move the decimal over, 28.15. Percent zinc, that's a Z. Okay, now we take this, 2 times 35.45, so that's 70.9, divided by the molecule's mass, and multiply all that by 100. So multiplied by 100. So it's 30.52% chlorine. Okay. $95.99 divided by the mass of the entire molecule. Then multiply by 100, 41.33% oxygen. So basically you would have had to do all 3 of them in this case. Did you need something, Bob?
Yes.
What?
I want some money so I can go get something from the vending machine.
Can you not wait while I do these 2 problems?
That's what I'm doing. I'm waiting
Okay,
for
but
you.
you're staring at me right in my face and it's weird. Okay. Next, what is the empirical formula of a compound that is, so they're giving us a percentage and we're trying to find out the empirical formula. So what we do is we assume 100 grams. So if we assume 100 grams, we can just convert these to grams. So we have carbon and we have oxygen. So we have carbon and oxygen. Okay, so I'm just going to go ahead and convert this to grams. Okay, so we have 27.3 grams of carbon, and we have 72.7 grams of oxygen. Okay, now we need to convert to moles. Remember, that was our first step. We need to convert to moles. So 1 mole of carbon, 1 mole of oxygen. So whatever's up here must go here. Grams of carbon, grams of oxygen. So we just find out carbon has a mass of 12.011. Oxygen has a mass of, we don't even have to look anymore, do we? 15.999 grams. And we're going to find we're converting grams to moles. All right, so we have 27.3 divided by 12.011. 3 significant figures, so 2.27. That's how many moles carbon. And then we're going to do the same thing, but with the oxygen. 72.7 divided by 15.999. Three significant figures, 3. So the lowest is 2.27. So we're going to divide each one by 2.27. And find out what the whole numbers are, and that's our subscripts. All right, so this one should be 1, right? If I did these right. And then we have 4.54 divided by 2.27. Wow. That makes it easy. All right, so we have our subscripts. So it's C1, but we don't put the subscript of 1, O2. So the empirical formula is carbon dioxide. All right, our last question. So now we are going to determine molecular formula. So we basically first determine empirical formula like we did, but they give us a mass of that substance. So then we divide it by whatever carbon plus 2 oxygens would have weighed, and then we find out the whole number and then multiply the whole empirical formula by the whole number. So let's do it. So what is the molecular formula of a compound that is this percent phosphorus and this percent oxygen, and it has the molar mass of this? So this is what we're going to use later. So first we need to determine the empirical formula, which we did just here in the previous question. So we always assume 100 grams, so we're just converting the percent to grams. So we have phosphorus, So phosphorus, we have 56.38 grams. And we're going to convert that to moles. Phosphorus. And we will have grams of phosphorus. And then we will have oxygen, which we have 43.62 grams of it. So we have 1 mole of oxygen. So for every 1 mole of oxygen, we will have 15.999 grams of oxygen. For every 1 mole of phosphorus, we will have 30.974 grams of it. Now we're just going to calculate it to get the moles. So 56.38 divided by 30.974. 4 significant figures, so 1.820. Same thing here, 43.62 divided by 15.999. 4 significant figures, 2.726. Now we just divide. This is the lowest number. Divide by that lowest mole number. So this should equal 1. Good. I was hoping it wouldn't be a whole number. So it's 1, basically 1.5, okay? So what we do here in this case is we multiply by the lowest whole number that will make both of these numbers whole. So the lowest whole number would be 2. That would equal 3, okay? But we also have to multiply this by 2, which would equal 2. So then the empirical formula is P2O3. That's the empirical formula, okay? So what we need to do is find out how much it weighs, okay? So we have P, and we have 2 of them. We have O, we have 3 of them. We know oxygen weighs 15.999 because we've done this a million times. Phosphorus, not so much. Phosphorus is 30.974. Court's probably going to come in and tell me about this cat screaming outside. So we have 2 times 30.974 plus 3 times 15.999 equals 109.945. So now what we do, we have empirical formula mass and we have molecular formula mass. So what we're going to do is take the molecular formula mass from here, 219.9, and we're going to divide it by the empirical formula mass, which is 109.945. Which equals 2. So 2. So what we're going to do is we're going to take the empirical formula and multiply it by 2, which will make the molecular formula P4O6.